Thank you, Anderson, and thanks to the organizers, and thank you to be here this morning. Okay, in this talk, I'd like to give you an overview about basically a proof of convergence of the shadow tomographic protocols with respect to a quantum version of the Wasserstein distance that is a tool from optimal mass transport. And then we can apply that convergence results to the training of a quantum GAN. So this is the outline of the talk. I start with an introduction to a quantum version of a GAN, and then I briefly recall what classical shadows are in the context of quantum tomography, and then I defined the quantum Wasserstein distance that we can use to study the convergence of the shadow tomography. And finally, we can apply the results to the training of the quantum GANs. Okay, let me start with an informal introduction about the classical generative adversarial networks. Classical GAN is basically an adversarial game between two parametric models, often neural networks, and the goal is reproducing a probability distribution of data. So in this sense, we have a model that is the generator that generates sample data from a source of noise represented by a prior distribution over a latent space. And the fake data, so the generated data, are submitted to another model that is the discriminator, and the goal of the discriminator is distinguishing the generated data from the real data. And in this sense, the two networks are training within an adversarial game. So it's an application of game theory to reinforcement learning in this sense. And at the end of the training, where we have an equilibrium state in the sense of game theory, an Nash equilibrium, the generator learns to reproduce the real probability distribution of data. So in this sense, we have this min-max game. So the goal of the discriminator is to maximize the probability to recognize the true states, the true sample. Sorry, not the true states, sorry, the true samples. And of course, the generator is the other player within the adversarial game. So in this picture here, the discriminator seems to be a binary classifier, but in the original proposal by Ian Goodfellow, the discriminator returns the probability that a sample, data sample comes from the true distribution P data. So, and you reach a Nash equilibrium in this game, and finally you have a trained generator that is able to reproduce the true data distribution. So in the quantum realm, we can introduce a quantum version of the generative adversarial network, and here the goal is again reproducing a probability distribution, but described in terms of an ensemble of quantum states that are unknown. And here we focus on n-qubit systems. So the generator, in general, it's a parametric source of quantum states. For example, realized by a parametric circuit. In this example here, this is the typical example of the quantum GAN. The discriminator is based on a classical source of noise that is used to prepare the quantum states, the generated quantum states. And here we have the feature mapping representing the classical noise into quantum states. And we have also the parametric part that must be trained in order to reproduce the real quantum states that are, again, unknown. And the discriminator, in general, trains a parametric observable can be described in terms of a parametric observable. So we have a parameterized family of self-adjoint operators on our Hilbert space. And this parametric observable is trained in order to distinguish, to discriminate the generated state rho generated by the generator and the given true state. Okay, so we have, again, the training of a quantum GAN described in terms of an adversarial game, a two-player game. And here we have the loss function. So the point is that the discriminators try to select the optimal parameters in order to maximize the probability of distinguishing between real states and fake states provided by the generator measuring the observable A. So we have this min-max game in terms of expectation values. In this simple scheme, we have the general structure of a quantum GAN. And okay, here we have the fake state provided by the generator. And we have also sigma, that is the real state. So in this scheme, we have to imagine that here we have a quantum memory in order to store many copies of the true state. That is a mixed state, in general, representing an ensemble of pure states, for example. Again, we have to imagine here a quantum memory that must be available in order to retrieve, for the discriminator, to retrieve the copies of the true state that the generator must learn. Okay, the point of this, okay. Just indirectly. Is the generator has not the direct access to the real states, but he learned to reproduce the real states within the adversarial game against the discriminator. The point of this talk is substituting, from a practical sense, the quantum memory here with a classical memory where we have stored the classical estimators of the real quantum states obtained by quantum tomography, in particular shadow tomography. Okay, so let me consider the tomographic scenario, and okay, you know that the quantum tomography in general is a protocol, or a class of protocols that are aimed to reconstruct quantum states by means of measurements. And this is not a trivial task in general. And so a tomographic protocol can be described as a procedure like this one. We have to prepare many copies of the unknown state that we have to reconstruct. We have to perform some measurements, and then we collect the classical data. And by means of classical post-processing, we have to estimate the density metrics that best fit data, where data are the classical data obtained by the measurement process. So the efficiency of a tomographic protocol is related to how many copies of the true state we need to prepare and how many measurements we need to perform in order to obtain a good estimation of the unknown quantum state that we wanted to investigate. Okay, we have here typical applications of quantum tomography. And in particular, we focus on the shadow tomography. That is not so recent, because it's been proposed 5 years ago, but I think that it's more recent than it should be, considering the long history of quantum tomography. So let me summarize the shadow tomography and the notion of classical shadow in this sense. So we have an ensemble of unitary operators, quantum gates, or in any case, an ensemble of unitary evolutions of n-qubit system. Again, we focus on n-qubit systems, but this machinery can be generalized to more general quantum states. But the description in terms of qubits is particularly effective and convenient. And okay, we need that the ensemble is tomographically complete. So basically, it's the property that it's able to reconstruct the entire state, roughly speaking. So, and these three steps are, in short, what shadow tomography does. So we have to sample a unitary from our ensemble, and we can apply this unitary evolution to our unknown quantum states that we have prepared. And then we simply measure each qubit with respect to the computational basis. So the outcome of this measurements is simply a classical string of n bits. And then we can apply to the collapsed states, that is nothing but a state of the computational basis, obtaining this inverse evolution. And this is a classical procedure, it's a classical computation, because we have simply to compute the action of a unitary matrix over a vector of the computational basis. And we can repeat on many copies of the state we wanted to investigate rho, these three steps. And in this sense, this procedure, the repeated procedure above, produces an ensemble of these classical objects that we can store in a classical memory. And by means of this ensemble, we can define the map M acting on quantum states, taking the expectations over the unitaries of our ensembles and over the bit strings of length n. And we obtain by this definition a convex linear map on the convex set of quantum states of n qubits. And we can extend this convex linear map here to M as a linear map on the operators over the n-qubit Hilbert space. And we can check that M defined in this way is an invertible map, and the classical shadow of the quantum state rho is defined as the pre-image by means of m to the -1 of our classical inverse evolved state. So the point basically is, okay, here we have a sort of operative definition of M in terms of these expectations, classical expectations, and then we can define its inverse. However, the point is an analytical computation of this map here. Because if we have an explicit and closed form of M to the -1, we can compute we obtain the classical shadow rho hat by means of a single measurement over the evolved state. Because we have an evolution sample for the ensemble, we have the outcome of the computational measurements. So in this sense, a classical shadow rho hat of the quantum state rho can be constructed out by a single unitary and a single outcome of a single measurement once provided an explicit form of the inverse of M. And fortunately, it's a pleasure to present this example because in some cases, and are also interesting cases, providing an explicit form of the map that you need to construct the classical shadow by means of a single measurement can be computed explicitly. For example, if U is the ensemble characterized by the uniform distribution of the Pauli matrices in this sense. So the Pauli operators defined in this way. So Pauli operators as the tensor product of Pauli matrices. And we have this ensemble of unitaries. And for this ensemble of unitaries, and of course, again, the computational measurements, we can define this action of m to the -1. So again, we pick up a unitary of this form for our ensemble. We can evolve the unknown state. We perform a computational measurement. We obtain our classical strings. And by means of the outcome and the unitary sample from the ensemble of unitaries, we can obtain, by means of a single measurement, our classical shadows. So the price to construct a classical shadows by means of a single measurement is constructing explicitly an analytic form of this map. But for example, here, it's done. Okay, and we have this the theorem presented by the authors of the original proposal of the classical shadow protocol. And if we take m observables and n classical shadows of the unknown quantum state rho, we can estimate any expectation value over rho up to an error epsilon by means of a number of shadows that grows logarithmically in the number of observables that we need to estimate in terms of expectations. And maybe you know that in the original proposal, in practice, we have the collection of shadows divided into k subsets of r shadows each. So that where there is here the expectation of any observable with respect or over the empirical means of the classical shadows of each samples of our k samples of classical shadows, and then we have the median of these means. So this is the median of means protocol proposed by the authors in the first in the original paper where they proposed the shadow tomography. Okay, so now I'd like to discuss where we can consider the quantum version of the optimal mass transport theory, in particular definition of the Wasserstein distance for quantum states, and we can provide a characterization of the convergence of the shadow protocols to the true states with respect to this distance, the quantum version of the Wasserstein distance. So let me introduce some basics of quantum optimal mass transport in this sense. Okay, the optimal mass transport, we have the original formulation of the problem is how to transport a mass distribution, physically a mass distribution. In fact, originally in the work of Monge, the old one, the optimal mass transport is basically construction theory, construction of buildings, is a civil engineering in this sense. But in the 70s, Kantorovich and Kumans applied the optimal mass transport to economics, and they won the Nobel Prize. And okay, but in general, from a more abstract viewpoint, in statistics and machine learning, we need, in general, to define useful distances between probability distributions beyond the weaker notion of divergences. So the divergences are useful tools, but in some cases, we need true distances. Example of divergence is the well-known Kullback-Leibler divergence. Here, for example, we have the Kullback divergence, Leibler divergence for continuous probability distribution. And in these three examples where we have a red probability density and a blue probability density, the Kullback-Leibler divergence is not able to quantify the similarity of these probability densities here, because of basically non-matching support of the densities. So in this sense, the people want to define true distances between probability distributions. And optimal mass transport is a way to introduce distances, notions of distance between probability distribution. In particular, we focus on a simple case where we have a finite set, and we consider probability distributions over a finite set. And we taken two probability distributions over a finite set, we can define the notion of coupling as a joint distribution such that the marginals are our two considered probability distribution P and Q. So if we take P and Q, we can define the set of their couplings in this sense. And the Wasserstein distance, at least in this finite scenario, can be introduced in this way. We need a distance over the set where we consider probability distributions. So take a distance over the finite set X. And the Wasserstein distance of order alpha is defined in this way. We have a sort of weighted mean of the distance of a power of a distance over the set where the weights are provided by the coupling. And we take the minimum over all the couplings between the distribution P and Q. And the Wasserstein distance is a good distance between probability distributions. At least, of course, there is also the generalization to the continuous distribution. But this is particularly important to present the quantum version, where we have no probability distributions over finite set, but we have quantum states. In particular, let me consider the dual formulation of the Wasserstein distance of order 1, the so-called W1. And the W1 distance, that is the object constructed in this way with alpha equal to 1, can be defined equivalently by duality with the Lipschitz constant of a function. So we define the W1 distance by duality in this way, taking the maximum over the function with Lipschitz constant at most 1. Let me focus on the Hamming distance. So take the finite set as the set of the binary strings of length n, and over X, we consider simply the Hamming distance. In this way, we can define the W1 distance over X with respect to the Hamming distance. Okay, now we can imagine to generalize the notion of Wasserstein distance, at least of order 1, to the quantum realm. Okay, we can consider the Rubinstein-Kantorowicz duality, and we need to introduce yeah. Can you repeat? Sorry, for no. Yeah. Yeah. Okay, and so let us consider a quantum version of the Lipschitz constant and define the W1, the quantum W1 by duality. Okay, so take a self-adjoint operator of n qubit observable, and the quantum Lipschitz constant is defined in this way. It's a measure of the local dependence of an observable age, because here we have this equivalent between the partials. So take two states of the n qubits, and we can trace out the qubit x. And in this couple of states satisfy this property. If we discard the qubit x, the two states are, once discarded the qubit x, are indistinguishable. then we can, if we compute this expectation value, the expectation of H with respect to the difference between the two states, we are measuring, we are quantifying the dependence of the observable over the qubit X. Okay, we can take the maximum over all the qubits, and in this sense, we have a measure of the local dependence of the observable over the qubit system. And this is the quantum version of the Lipschitz constant for this reason. Take a function, a real function defined over our finite set, and define directly a self-adjoint operator over your n-qubit states, that is self-adjoint in particular diagonal with respect to the computational basis. And once you have defined this self-adjoint operator, this observable, you can check that this object here for the observable F coincides to the to the classical Lipschitz constant of the function small f. Okay. I don't understand this maximum of x. So you maximize this function such that there is like one. So it's x. Okay. This is the maximum over all the qubits. So for any qubit, you can evaluate the dependence of the observable over the qubit X. Now, for one qubit, let's say if you trace out the first qubit, then the row is on the right side, and then that's fine. Okay. Okay, great. This maximum here is taken over the couple of states satisfying this property here. And this X, the entire set, like 1, 2, 3, 4, 5, 6, up to n, or is it enough to exist one point in the set where they coincide? So this is single set. This maximum is taken over all the sites of your qubit system. No. One qubit. No, this is not a region of your qubit lattice. Okay, it's a single qubit X. So here we have okay, great. Thank you for the question. It's an important clarification. So Giacomo and the co-authors introduced in this way the quantum versus time distance over the one. We have a notion of quantum Lipschitz constant, and then the W1 distance is defined by duality with respect to the quantum Lipschitz constant, taking the maximum over the observable with Lipschitz constant at most 1. And this is a good, the Lipschitz constant is a measure of the local dependence of an observable over your qubit systems. So in this sense, this is a distance among states that measures the local distinguishability of states. But there is a shortcoming in this formulation. In fact, 2 years ago, Giacomo and Dario proved that the von Neumann entropy is continuous with respect to the quantum W1 distance defined in this way. So, however, in general, there are pure states with a certain degree of entanglement that are locally indistinguishable to the maximal mixed states. So we have that two locally indistinguishable states with different value of von Neumann entropy. And in this sense, they are far from each other with respect to the W1 distance. So the point now is an improvement, let's say, of this distance in order to measuring better, in a better way, the local similarity or distinguishability of quantum states over n qubits. In this sense, we define the so-called local norm. How much time do I have? Great. Thank you, Anders. Again, take an observable over n qubits, and we can define this object in order to, again, quantify the local dependence of these observables, but in a different way. So we consider the local decomposition of the observable, so as a sum, and here we have the regions of the n-qubit systems, this subset here. And H is a sum, expressed as a sum of local terms. So H, small h lambda is a self-adjoint operator here. So it's a self-adjoint operator acting non-trivially, so the action is not the identity, only in the region lambda. And we quantify the dependence of H over the qubit X, taking the sum of these operator norms. Here we have the standard operator norm of any local term. But we introduce these coefficients with this order relation here, in the sense that these coefficients has the role to penalize the terms with local terms acting non-trivially on a large number of qubits. Because when you take the minimization outside, these terms are penalized by the choice of these coefficients here. So it's basically a tool specifically introduced to measure the local dependence of the observable. So it's quite artificial, but we had in mind the application. Okay. It's the same to what? Okay, I'm not so sure, but probably it's related in some way. Okay, good suggestion. No, you're right. Okay. No. Okay. Okay, so let me take, so 2 is just a prefactor for normalization reasons that I don't discuss. But okay, we take this local norm, and again, let us define the local quantum W1 distance by duality with respect to the local norm. And this is an improved measure of local distinguishability of quantum states. Improve in the sense that it measures in a better way the local distinguishability with respect to the W1 distance introduced earlier. Okay, we have these results presented with Giacomo and Tristan. We collect, and we can collect n classical shadows of an unknown n qubit states, and we can compute the empirical mean of these shadows. In this sense, we have not a median of means, we have precisely the empirical mean of all the classical shadow that we have collected. And so there exists a choice of these coefficients such that we have these convergence results. So we can construct the our W1 local distance in order to have this result. So we can obtain a good estimation of the true quantum states in terms of the empirical mean of the classical shadows by means of in the W1 local distance by means of a number of shadows that grows logarithmically number of qubits. And this is the point for the application to the training of quantum generative adversarial neural network that we are going to discuss. Is there a question there? For any, what do you mean with particular norm? So, okay, for any choice of these coefficients satisfying this ordering there, we can define a multi-parametric family of local norms. In this sense, yeah. There is an explicit form of these coefficients that that I'm not presenting here in order to obtain these results of convergence. Yeah. Okay. No. This is a very good point that I omitted in this slide, but okay, thank you for. It's an important point. Okay, now let us come back to the quantum GAN, and we try to apply these results for characterizing the training of a quantum GAN, where we consider not, so where the generator does not access the true state, the true quantum states to learn, but access only the estimation, a shadow estimator in this way. Okay, so this is the quantum GAN in its that I mentioned also earlier in this original form. We have the parametric states where theta g are the parameters of the generator model or the generation model. And sigma is the true state, in general mixed state, of course. And here we have the parametric observable tuned by the discriminator. And such that the observable in this parametric family have operator norm at most one. So if the discriminator has a sufficiently large family of observable with this property, he's able to obtain a good estimation of the trace distance between the states in order to discriminate the true state and the fake state. However, in general, this training of the model, that is the original one, suffers from barren plateaus. But there exists an improvement in order to mitigate the barren plateau phenomenon. And it's the point of using the quantum Wasserstein distance instead of the trace distance in order to discriminate the states. And okay, so using the Wasserstein distance from optimal mass transport for generative adversarial networks is well known also in classical scenario. So it's quite common training GANs with the Wasserstein distance in classical machine learning. But in the quantum case, the quantum Wasserstein distance to train the quantum GANs is important to mitigate the barren plateau phenomenon. So here we have basically the only change with respect to the previous case is that here the discriminator has a parametric family of observables satisfying this property here. Not we have the bound over the Lipschitz constant, and instead of the bound over the operator norm. Again, if the discriminator, has in his hands a sufficiently large family of parametric observable, he can estimate the Wasserstein distance between the states in order to discriminate. Yeah. We are coming there right now. Okay. Okay. This is your question. This is the answer to your question. Sorry. Okay. Good. But the complexity of the computation of the exact Lipschitz constant of the observables is exponential in the number of qubits, and of course the dimension of the space of the observable is exponential in the number of qubits. So in practice, the quantum Wasserstein GANs can be used by means of a proxy of the Lipschitz constant and the Wasserstein distance in this way. So we take only, we can consider the key local Pauli operators on n qubits, where K is the locality in this sense. So this Pauli operator acts non-trivially on at most K qubits. And the K is big O1 in N with respect to N. And so we can define the set of K local Pauli operators on the system of N qubits. And in particular, we can consider this family of observables, of this set of observables. So the self-adjoint operator given by the linear combination of the K local Pauli operators of N qubits. And then we have this proxy of, let's say proxy of the Lipschitz constant of a K local and qubit observable. And in turn, we have also the proxy of the local Wasserstein distance of order 1 for the discriminator. And it's basically the definition that we have already introduced, where here we have only the K local observables, and here we have the proxy of the Lipschitz constant. Yeah. Down on the surveys that infinity or whatever is that no, maybe I didn't see the point, but can you repeat? The standard operator norm. The reason why using this the Lipschitz constant instead of the standard operator norm mitigates the barren plateau phenomenon. Is it your question? No, the point is that the discriminator prefers to use the Lipschitz constant instead of the operator norm, because the quantum Wasserstein GAN is more robust against barren plateau phenomena. Yeah. Thank you for the intuitive insight. So it's right. Thank you, Eric. Okay. And then the discriminator compute or estimates this proxy of the W1 distance in order to distinguish the fake and the true states. Just a remark, the Wasserstein, the quantum Wasserstein GAN, for example, is able to learn complex state, such as the n-qubit GHZ. The approximated one. Okay, so what about the training of a quantum GAN in terms of classical shadows? So we have this proposition here, proved in the same paper, where the distance that is called Earth mover distance, this proxy of the W1 distance is upper bounded by this CK is one of the coefficients that we have introduced in the definition of the local norm by the local W1 distance that we have introduced. So these results, together with the results on the convergence of the shadow protocol in the local W1 distance, provides these results here. So if no a priori information, under this assumption, about is known about the true state of the n qubits that we have to learn by means of the quantum GAN. So the quantum GAN, or in particular the quantum Wasserstein GAN, can be trained over a small number, small in the sense that it grows logarithmically in the number of qubits, classical shadow of the sigma. This is the true state. So in this sense, so if we have a Wasserstein quantum GAN, we can equivalently learn the model considering classical shadows of the true state instead of the true quantum states over we have to perform the measurements, retrieving at any round of the protocol, of the training phase, the true state or a copy of the true state from a quantum memory. Okay. Oh, I don't know, it's the first one. Yeah, no. It's one of the coefficients relative to the convergence results, and K is the K specific of the Earth mover distance. That is the locality of the observables. Allow to have this estimate for all the local densities. And see this, I guess one can also say something like if one defines an average matrix over all the local density matrix, doing the standard like applying the known theorem of Pauly-Short homotopy, can estimate the things that are according to this average matrix of local density matrix distance. And this document lot that we defined seems to be something it says to be locally equal. I mean, in this transition, can one use this in order to put this theorem, or like Pauly-Short homotopy allows you to estimate the precision all local power. Yeah. So local density. And to this, can you go to this theorem, to this what you want now or not? Okay. I'm not sure that it's the same, the really same thing, but I think that it's reasonable. Are two related concepts, but I'm not sure that you can arrive to the same results from your proposal. But we. No, no, I'm not sure I have understood your point. Can you repeat the okay? Yeah. Yeah. Yeah.
There is some relation with this local
yes, in some sense, it's yeah, it's similar, yeah, because you consider the empirical mean of the classical shadow. So, and in this sense, it's similar to what you are saying about your mean. So roughly speaking, I think that it's related, it's closely related, if I correctly understand, but maybe we can discuss. But if
the local density the local density while for me it's not really okay, why
maybe you can discuss it. Ah, okay, yes, sorry. 1 minute. You have a lot of time. Okay. Okay, and so okay, I have 1 minute, so I have to skip the last part, but it's quite off topic because the same machinery of the local Wasserstein distance can be used for providing some thermodynamical results about the equivalence of canonical and microcanonical ensembles for n qubit or n spin systems beyond the qubits, also p spins. And supporting that, this is the results that I have to skip, but supporting the point that this local Wasserstein distance is crucial. It's remarkable to describe statistical local properties of states, both in quantum machine learning and neural networks and in thermodynamics, but the two frameworks are not independent. We know also in the classical case. Conclusions. So we have the sort of shadow training of a quantum GAN, and this a suggestion of a practical aftermath of these results. That is that the quantum memory is the available quantum memories are not robust against noise. For example, the most recent quantum prototypes of storages has a occurrence time of 10 seconds. So it's I think it's good if we are able to store classical data in a classical memory in order to train a quantum model, because after the training you have a true quantum model to run. Other applications are related to concentration inequalities and equivalence of thermodynamical ensembles of the quantum W1. And future perspective, it's quite vague. It's very general insights about future perspectives. So further applications of the local W1 in quantum machine learning, because it's related to the quantum tomography, and probably it's important to have classical estimations of quantum states in order to effectively train quantum models. Thank you for your attention.
Before, I guess, so
I just want to know how your local distance related to, so I mean, obviously it's going to have something, you want to try and up and lower bound it in terms of like standard tricks on distance, but just because you learn locally does not mean you've actually done.
Yeah.
What about NLP loss?
No, I don't know. No, I see your points, but I have not an answer yet. We can discuss about that. It could be interesting. Hello.
the W can learn GZ state.
Yeah.
But with respect to the local Wasserstein GAN, what would that really mean? Like, if I just learn a maximum mixed state, would that be low Wasserstein GAN distance to low Wasserstein distance, local Wasserstein distance to the GZ or not? You know what I mean? Like with respect to
Maybe I'm not sure about your perplexity.
I don't.
Locally, where then basically not
Okay.
I don't see that we could learn it well with respect to first distance because the GZ with a plus and the GZ with a minus, I don't think they're distinguishable from this local measurement.
Okay.
Right? And your Wasserstein local Wasserstein GAN, it's actually only looking at reduces the
I see. Okay, okay. I didn't work directly on these applications. I just reported it as a remark, but it's not a result from myself. So probably I can.
the claim with respect to the local Wasserstein.
They parallel with that, would be by hand the product of X over every few bits among the observer, also the discriminator. Okay. That's how you distinguish between the GZ with the plus and the GZ with the minus.
Okay, so you add to the distribution.
Yes, because otherwise, with respect to this distance, they are not distinguishable.
Exactly. And you have
And once you do it, then you learn increase distance.
once you add the proposed X effect, apparently learn these all of those.
the training doesn't include that.
It does.
Well, yes, it does. In my hand, exactly for that reason. Otherwise, you can distinguish between the plus and the minus.
So that works for GXV, but then do you have to pick by hand the additional global values?
Yeah.
Yes.
So if you do that, you don't get a signal from it, probably because you won't get a signal from different BPs.
Yeah. Yeah. Variable follows will in general, when you have put the additionally to your cost function, that thing will suffer from that term is funded by because it's low. But yeah, I think we can move it.
Yeah, maybe just use systems for is there any example of training stages of model, for example? So building it to be a force of say any kind of gratification. And the other question is in the other line something that use differently use tomography and yeah. Then discussion leads to quantum computation. So is always the case, or you want to use tomography when you use the quantum method, or it is the best way to find that can find it.
So about your first question, it's exactly what I mean when I point out that future perspective of this work about quantum machine learning is exactly in this direction, in that direction. And about the second one, what do you mean exactly with? Yeah.
Is this always the case? I don't guess the question, right?
Yeah.
So because usually for example, so is there so you always have to use one when you do the one.
But as far as I know, I'm not able right now to provide another examples of a quantum model where we have an effective training in terms of tomographic estimators. But I would be very surprised that if the training of the quantum GAN is the only example where we can use tomographic estimators to train the quantum model. In this sense, the answer is related to the answer to your first question, where I think that we have to investigate in deep the application of quantum tomography with respect to this distance or other distances for the training of quantum models in terms of classical estimators. I don't know if I have answered your point. Okay, great. Thank you very much.
Black hole.
Wow.
Okay, this,